All right, let's go after a second problem here. What we have is a water tank. So here's our water tank. It's a circular water tank, and it's got a drain at the very bottom. Now, initially, at time t1, or 0 seconds, t1 equals 0 seconds, the height of water, H2O in the water tank, is equal to H1, or if you like, 1 meter. So originally, we have a depth of 1 meter of water in this water tank. Okay, and it's a circular tank. The cross-section area of the top of the tank is equal to A tank. So it's a circular tank. The top cross-section area is A tank, and that's equal to 2 square meters. So it's a 2 square meter area tank with a height H. Now, the flow out of the bottom drain, and it's a circular drain out the bottom, the flow out the bottom is equal to the flow area, A out. So this is a circular pipe coming out the bottom, and it has a certain flow area. The mass flow rate out the bottom is equal to the flow area for the outlet times the velocity at the outlet times the density of the water. So we have flow going out of this bottom drain, and the bottom drain has a certain cross-section area and a certain flow rate or flow velocity, VEL out. The outlet velocity through the drain is proportional to the square root of the height of water in the tank. The more water there is in the tank, the more flows out the bottom. So as the water approaches a 0 level, H goes to 0, the flow rate goes to 0. So the outlet velocity at the drain is the square root of 2 times the gravitational acceleration, 9.8 meters per second squared, times the height of water in the tank. So you're given this expression for the outlet flow velocity. So we start off with a certain height of 1 meter in the tank. Pull the cork, water starts to flow out the drain to the bottom. We want to know how long it takes to drain the tank down by 90%. In other words, H2 is equal to 0.1 meters. The height, H2, the height down to 1/10 of a meter. How long does it take to drain 90% of the water volume in the tank? What is T2? Okay, so the velocity and therefore the flow rate at the outlet is going to change with time. So clearly we're going to have to do some integration here to figure out how long it takes to drain the tank. Okay? All right, so let's get started here. How long does it take to drain 90% of the water out of the tank? Here's our system or control volume. Oops. So there's our system right there. And clearly we have mass flow crossing the system boundary at the outlet. So this is the outlet here. There's no inlet. The system is composed of the H2O, the liquid H2O, so the system is shrinking. The volume of the system is shrinking over time as we drain some of the fluid out, all right? Okay, so we've defined the system as encapsulating the liquid H2O inside of the tank, and over time flow, or H2O leaves the system at the outlet at the bottom. We want to know how long it takes to drain 90% of the H2O liquid away, starting off with an initial height of 1 meter. Okay, let us apply the mass balance to this open system. We have one outlet, so clearly this is an open system. So analysis. So we have an open system. So let's write conservation of mass down for our open system. The change in mass within the control volume with respect to time is equal to the sum m dot in minus the sum m dot out. All the inlet flow minus all the outlet flows from the various inlets and outlets. Now in this case, we don't have any inlets. The control volume is that surrounding the liquid H2O in the tank. So we don't have any inlets, but we do have an outlet. No inlets, but we do have an outlet. No inlets, so this is 0, but we do have an outlet. Now the mass flow at the outlet is going to be equal to, so this is m dot out. The mass flow at the outlet is going to be equal to the density of the water. The density of the water times the flow area times the velocity at the outlet. Velocity times the flow area, that gives you a volume flow rate, times the density, and that'll give you m dot. So V dot out times the density at the outlet, and V dot out is the flow area times the velocity, VEL, at the outlet. In other words, A flow, VEL out times the density of the H2O. So rho out is the density of the H2O, okay? I guess I'm calling the area, I'm calling this A out, I guess. Keep my nomenclature the same, the outlet flow area. All right? So I have the time rate of change within my control volume of mass is equal to, and I have an outlet, so I got to carry the negative sign. I have A out, velocity out, density of the H2O. Okay? Density of the H2O. Maybe I should put some assumptions here. I'm going to assume the density of the H2O is the same. It's a liquid. So I'm going to assume density is constant. This will come into importance in just a moment. So assumptions, rho H2O is constant. In other words, incompressible. So the liquid H2O doesn't change density over time. Okay, so I'll write up my first assumption there. Now, what is the mass of H2O in my control volume? Well, that's going to be equal to the volume of the tank times the density of the H2O. So V tank times density of the H2O. Density times volume gives you mass. Now the volume of the tank is going to be equal to my height h times the tank area. The tank area times the height gives me my volume for the tank. So V tank is A tank times h, and then I have rho H2O, okay? So let's write what I got here. dmCV dt is actually d vol tank, or d area tank times the height times the density of the H2O. And then I have a dt. This is mass within my tank, area tank times h times density of the H2O. That's the mass within my tank. So d A tank h rho H2O dt is equal to minus area of the outflow times the velocity of the outflow times the density of my H2O. Okay? Now, we're given the tank and the flow area. The tank and the flow area are constant, 3 square centimeters for the tank, for the outlet, and 2 square meters for the tank surface area. And we're also assuming H2O density is constant. Constant tank area, constant flow area, constant density. So because the tank and the tank area and the density of the H2O is constant, I can pull them out of the derivative. So I get A tank rho H2O dH dt is equal to area out, velocity out, rho H2O. Notice the densities cancel. So density doesn't even figure into the problem. Density doesn't even figure into the problem. And also, let's make our substitution for the outlet flow velocity at this point. VEL out is square root 2 times the gravitational constant times h. The greater the height of H2O in my tank, the greater the outlet velocity. It's not quite linear. It's to the half power for h. So let me make the substitution here. Let's see, the outlet flow velocity. We are given, this is square root 2gh. Okay? So let's write out what I have. Area tank dH dt is equal to flow area of the outlet, 2gh, and the density terms are gone. Okay? So let me solve this for dH dt. The time rate of change of height within the tank is equal to the ratio of A out over A tank, the ratio of the outlet flow through the drain, flow area through the drain, and the tank area, square root 2gh. Okay. So this is an important equation. Let's call it equation number 1. And I'm going to erase some of this stuff over here. Application of open system mass balance. So we have a differential equation there. Equation 1, which gives me the rate of change of height within my tank. It's a differential equation. How do we get the amount of time it takes to drain the tank by 90%? Well, we're going to have to integrate this equation and then plug in the various h values as well as our areas and the gravitational constant. So let's integrate equation 1 from T1 to T2. So integrate 1 from T1 to T2, or if you like, H1 to H2. Okay, let's integrate. Now, one little thing to do here first, is I'm going to separate variables. I'm going to take the dt and put it over here, and the square root h and put it over here. So we're going to separate variables. So I'm going to rewrite equation 1. So let's rewrite equation 1, and we have the h's on the left and the t's on the right. So dh, and then I'm going to divide both sides by square root h. The square root h goes away on the right and appears on the left. So I have a out over a in, and then I have a square root 2g. And then I'm going to take the dt and put it over on the right-hand side of the equation. So I have a dt right there, okay? That can be integrated. That can be integrated. from H1 to H2 and from T1 to T2. That can be integrated. By the way, T1, the initial time, I've defined T1 to be equal to 0 seconds. T1 is equal to 0. I want to know how long it takes, in other words, T2 to drain the tank by 90%. So I guess I may as well set this equal to 0 right now, okay? T1 is equal to 0. I want to know time T2, in other words, how long it takes to drain the tank by a certain amount. So let's integrate this here. Well, the antiderivative of 1 over the square root of h is 2 times the square root of h, evaluated from h1 to h2. The antiderivative of 1 over square root of h is 2 square. If we can check this, you take the derivative of the square root of h, the 1/2 pops out, the square root h goes to the denominator, and the 2 in the numerator cancels out with the 1/2 or the 2 in the denominator, and you get 1. So this looks pretty good. 2 times the square root of h. And then the areas are all constant. 2 times the gravitational constants are all constant. They can be pulled out of the integral. And I get area out over area tank, square root 2g. And then I have t evaluated from T1 equals 0 to T2. Okay? So let's plug in here. Let's plug in the limits and let's see what we got. Let's plug in the limits and we'll see what we got. We're running out of chalk here. There we go. Let's see here. 2 times square root h2 minus square root h1. Okay, plug in the limits on the left-hand side, and then I have a out over a tank. Square root 2g. Plugging in the limits for t here, I get t2. T1 is equal to 0, so I'm just going to let that go away. All right? So let's solve for T2. The time at state 2 as a function of various initial and final heights is, let's see here, 2 square root h2 minus square root h1. And then I've got divided by a out over the tank area. And then I got square root 2g. Now I can divide both sides by 2. Oh, I'm sorry, and this is equal to T2. Okay? So the time, and we'll flip the equation in just a second, get T2 on the left-hand side. So the time T2 to drain the tank is a function of these various initial and final heights and the gravitational constant and the ratio of the flow areas. Let's get rid of this 2 here. This doesn't look good. Let me divide top and bottom by 2. And I get square root h2 minus square root h1. And then I get what? A out over a tank, and then I've got square root g over 2, gravitational constant over 2, okay? Divide top and bottom by 2. Becomes a 4, or a 1 over 4 when you pull it into the square root, and that cancels out partially with the 2 in the numerator. That's where the g over 2 comes from, okay? So let's write down the final expression here for time t2. And then we can plug in numbers and figure out exactly how long it takes to drain the tank by 90%. Okay, let's see here. So T2 equals square root H2. Oh, I forgot a negative sign. Let's see here. That would have been, remember we had a negative. I dropped the negative sign. We had a negative m dot out. So there's a negative sign floating around here. Just put it in front of, just put it right here, okay? There's the negative sign right there. Getting a little sloppy. There's my negative sign, square root H2 minus square root H1. Negative sign, okay? And then I have area out over the tank area, square root gravitational constant divided by 2. Now, we have the heights. We have the height h1, which is 1 meter. The height h2, which is 0.1 meters. Did I include that? I did not include that here. h2, 0.1 meter. So we're going to lose 90% of our volume and therefore mass. I have my h1, I have my h2. I have my outlet and my tank area, the surface area for the tank, and the flow area for the outlet flow. I've got all that. G, of course, is 9.8 meters per second squared, so I can plug that in just a moment. Okay. So we got everything. Let's plug in. Negative square root h2. Let's see, h2 is 0.1 meters. h1 is 1 meter. And then I have the ratio of area out to area in. Let's see, the outlet area is 3 centimeters squared. And the tank area is 2 square meters. The surface area of the tank. It's a cylindrical tank. Apparently, its top surface area is 2 square meters. I have some unit problems here. I need to get these areas in the same units. So there is, for every 1 meter, there is 100 centimeters, and I'm going to square that. I get centimeters squared, and that will cancel out with the centimeters squared in the numerator, denominator, numerator, and I will get meters squared in the equation, okay? And then I have my square root G over 2. So I got 9.8 meters per second squared, and then I'm going to divide that by 2. Let's crank the numbers out here and see what we get. Let's crank the numbers out. Let's see here. So we get negative. I get the numerator and I get negative 0.68, and that will have unit of square root meters. Square root meters, so that's my unit. And then I have, let's do the denominator here. So let's see here, give me a second. So 9.8 divided by 2 times 3 divided by 2 divided by 10 to the 4th. So I get 3.32 10 to the minus 4. That's the 100 squared there, so that's 10 to the minus 4. And the areas cancel out for the units, and I get square root meters per second squared. That comes from the acceleration term with the square root. Now let's look at the units here before I plug in and get the final answer here. The meter here cancels out, the square root meters cancel out in the numerator and the denominator, and I end up with 1 over square root seconds. That's going to go up in the numerator. Square root seconds will go up in the numerator, and my final unit will be seconds. So let's cancel this here. I did it again. Negative times a negative, that will be, sorry about that, that will be a positive sign. Sorry about that. Square root 1 meter is greater than square root 0.1 meters, so this quantity in brackets is going to be negative. So we get 0.68 divided by 3.32 times and I get 2,048.2 seconds. Let's just make sure that's right here. Let's see here, 0.68 divided by 3.32. Yeah, times 10,000. That should be fine. So that is seconds. Let's write that in minutes here. Let's see here, divide by, divide by 60, and that gives me 34.1 minutes. Or if you want it in hours, 0.569 hours, okay? The unit conversion here, if you want to do the unit conversion, let's see here, there is 1 minute per 60 seconds, and there is 1 hour per 60 minutes here. So that's how we do the units, okay? 34 minutes to drain the tank. Let's write that down. T2, 34.1 minutes. That's my draining time. That's my draining time to drain the tank. Okay, so this is an unsteady. This is an unsteady problem. We're actually draining, we're removing mass from a control volume, removing mass from our system. So the amount of mass is changing with respect to time in the control volume. So it's an unsteady problem. dmCV dt is not 0. So this is a cute little problem, cute little unsteady problem for you to chew over, okay? 34 minutes to drain the tank. This is a pretty complicated problem. I don't think most of your problems you're going to do are going to be this complicated, but it shows the power of conservation of mass applied to an open system, okay?